Okay, so today we're going to be looking at some more analytical applications of the fundamental theorem of calculus, part 1. And so we're going to start off with this prompt. The graph of a differentiable function f on the closed interval 1 to 7 is shown below. Let h of x be the integral from 1 to x of f of t dt for 1 to 7. So this is a function defined by an integral. So h of x is an integral, and so this is a very common problem that appears in calculus. So we have this graph. This graph is of f itself, and so h of x is the integral of this function f, and so it'll be the area dealing with this function, the area under this curve or between this curve and the x-axis. So let's go ahead and we're going to start with part A. So part A says we want to find h of 1. And so if I'm finding h of 1, that means I'm going to be plugging in 1 for the x coordinate. So h of 1 is going to be equal to the integral from 1 to 1 of f of t dt. So we know by our definite properties of integrals that if you take the integral from some bound to the same bound, your integral would be 0 because your area would be 0. That's like asking me to take the area under this curve from 1 to 1. Well, it doesn't have any width, so the area of that, quote, rectangle would be 0, okay? So that's part A. Part B says find h prime of 4. So when we find h prime of 4, the first thing we should do is we should find h prime. So h prime, I'm going to do that up here. So h prime of x means we need to take the derivative of this function. So you need to take the derivative of the integral from 1 to x of f of t dt. And when, according to our fundamental theorem of calculus, when I take the derivative of an integral, it cancels out and I'm plugging in that x value. So what I end up with actually is that h prime of x equals f of x. Okay? And so then when it asks me to find h prime of 4, what I'm really being asked to find is f of 4. And so I'm just finding from my graph then, since my graph is f, I'm finding f of 4. So 4, 2. In part C, it asks on what interval or intervals is the graph of h concave upward or concave up? And so we have to remember some stuff from first semester. So concave up means a couple of things. In terms, if I'm looking for where h is concave up, I need to look at where h double prime of x is positive, or you can look at where h prime of x is increasing. So that's what we want to look for when we're looking for where your graph of h is concave up. Now, luckily, we already have some information about h prime. So I know that since h prime of x is f of x, I'm going to be looking at where these things are increasing. And so that happens if I'm looking at my graph. I'm just looking at where my function f of x is increasing. So I'll notice that my graph is increasing from 1 to 3. And then where else is my graph increasing? From 6 to 7. And your justification for that would be because h prime of x equals f of x, and f of x is increasing on those intervals. Awesome. All right, let's go look at part D. So part D says find the value of x at which h has its minimum on the closed interval 1 to 7. And then we have to justify our answer. So if we're looking for where h has its minimum, we would check any local mins and maxes first, and then we would also check our endpoints, right? Because it gives us a closed interval. And so we know a couple of things. Let's actually check our endpoints first, just because it'll be easier to start with 1. So if I find h of 1, we actually already did that in part A. So h of 1 equals 0. So that's a pretty low number. And then from h of 1 equaling 0, we have to look at what happens to h. So after h of 1 equals 0, we know a couple of things about your function h. So between 1 and 5, h of x is increasing. And that makes sense just from an area perspective, right? So if I start at 0 and then I am looking at the area under my curve, I'm gaining area, right? Area above the curve is positive. So without actually mathematically figuring it out, you can say that this area, A1, if we want to call it that, is positive, and then A2 is negative, but it's not very large compared to A1. So there's a lot of positive area and then a little bit of negative area. So between 1 and 5, h of x is increasing, and then between 5 and 7, h of x is decreasing, because you had some positive area and now you're subtracting some area. And so that would imply that somewhere on the interval 1 to 7, there is a maximum. Because if I have something that's increasing and then it goes to decreasing, there's a maximum. And we don't need to pay attention to a maximum point, because we're finding all the value of x at which h is a minimum. And so this basically cancels out the fact that there is no local minimum that you have to deal with, because we had a function that started at 0. It started to increase by, we don't know how much, but it was increasing, and then here it changed around and went decreasing. So that means that there is a local maximum. So no minimum that I have to worry about, which means my minimum is at one of my endpoints, right? When we do our candidates test, we usually compare, like we find h of 1, we look for any local mins, and then we check the other endpoint, h of 7, right? But for our scenario, when I was comparing A1 and A2 previously, right, we talked about how the first area was some positive large number. I know it's going to be at least, let's see, 5 plus some pieces, right? Because that's the area under my curve, are these 5 squares, and then plus some of these triangular pieces or curved pieces. And then my area below the curve is going to be some negative number, but it's not going to be a very large negative number. It's going to be like maybe negative 1 point something. So regardless of what h of 7 actually is, I know it's going to end up being some positive number. And so between all of my options for what's a local, for where its minimum value occurs, h of 1 equals 0, there are no local minimums, and h of 7 is some positive number. That means that there is the value of x at which h has its minimum on the closed interval is 1. So x equals 1. And then everything we wrote here would be justification for that. Cool. All right, let's go ahead and look at one more example. So in this example, the graph of a function f consists of a semicircle and 2 line segments as shown below. Let g be the function given by g of x equals the integral from 0 to x of f of t dt. And the first thing that we want to find is we want to find g of 3 and g of negative 2. So when I find g of 3, what I'm really finding is the integral from 0 to 3 of f of t dt. So I want to find the area under this curve from 0 to 3. So let's see, 0 starts here and then goes to here, which means I need to find this positive area up here, which is a quarter of a circle. So we'll do pi r squared over 4, and my r is 2. So 2 squared over 4. Breaking it up into 4 because the area of a circle divided by 4 would give you the area of a quarter circle. And then the area under your curve from 2 to 3 would be a triangle. 1 times 1 divided by 2 would be 1/2, but it is negative because it's below the x-axis. And so when I find my actual final answer for this, I end up with pi minus 1/2, because your 4's cancel, and then it's 1/2. So that would be what g of 3 actually equals. And then to find g of negative 2, we do the integral from 0 to negative 2 of f of t dt. And we have a little bit of an issue here because my lower bound is supposed to be lower than my upper bound. So I can flip this using my properties of definite integrals. And if I flip it, I just have to have a negative out front. And so then now I'm finding the area under my curve from not 0 to 3, but from -2 to 0. So I'm finding this area, which is still just the area of a quarter circle, which we already actually know over here. So pi r squared divided by 4 would give me just pi, but it has this negative out front. So negative pi would be your answer for that one. Awesome. All right, in the next portion, we are going to find the find all values of x on the open interval, which g has a relative maximum, and we have to justify our answer. So if I'm looking for g having a relative maximum, that means I need my g prime of x to equal 0 and change from positive to negative. So the first thing I should do is find g prime of x, and so g prime of x is the derivative of g, so I'm finding the derivative of this integral function from 0 to x, f of t dt. Derivative of this, plug this in, so then g prime of x is actually equal to f of x, this function. So I want to find where g prime of x, aka f of x, equals 0 and changes from positive to negative. So that happens here at 2. So at x equals 2, because f of x, and because I wrote this part, you don't necessarily need to write it again in the justification, right? I know that f of x and g prime of x are equal. So because f of x, if you want to write it, equals g prime of x, and equals 0 and changes from positive to negative. Part C says write an equation for the line tangent to the graph of g at x equals 3. First thing you should write down when you see equation of a tangent line is y minus y1 equals mx minus x1. Our x1 is going to be 3 because they give it to us. Y1 is going to be g of 3 because I'm finding the equation of the tangent line to g, so g of 3, which we luckily already figured out in part A. G of 3 is pi minus 1/2. And then we also needed to find our m value, which is g prime of 3, aka f of 3, right? G prime equals f. And then if I look at my graph, f of 3 is -1. So when I write my equation of the tangent line, I can write y minus, y1 is kind of messy, so I'm just going to leave it in parentheses like that, equals m x minus x1. There you go. All right, last but not least, find the x-coordinate of each point of inflection on the graph of g on the open interval -2 to 5. So if I have points of inflection on the graph of g, that means that g double prime of x equals 0 and changes signs, which means that g prime of x changes from increasing to decreasing or vice versa. Okay, so if I am finding the places where g prime of x changes from increasing to decreasing, I'm looking where g prime of x, aka f of x, does that on my graph. And so increasing to decreasing or vice versa. So increasing, 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 decreasing. So x equals 0 would be one of my places. Decreasing, decreasing, decreasing. Nope, still decreasing, 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 decreasing. Okay, so then x equals 3 because then it changes to increasing. And your justification for that would be because f of x, aka g prime of x, does this. Changes from increasing to decreasing or decreasing to increasing. Awesome. All right, so now that we have a little bit of the analytical practice under our belt, we can go ahead and work on some practice of our own.